Okay, let's continue our discussion of how we manipulate data in memory in the C language. Our next topic is going to be how we talk about arrays. Basically, arrays are adjacent locations in memory that store the same type of data object. So here I am, in this example, declaring an array of integers. Its name is big underscore array, and there's 128 integers in that array. That number between those square brackets. This is going to allocate 512 bytes of adjacent memory, starting at some location. What location? Doesn't really matter. The one I'm showing here is pretty arbitrary, but it'll be easy for us to use in our examples. But basically, the compiler will take care of that and decide where in memory that data should go. Now, our pointer arithmetic can be used for indexing in this array. So let's take a look at some examples here. First of all, let me start with just declaring a pointer to an integer type. And we're going to call that pointer array underscore PTR. Okay? Now, the very next statement says, let's take big array and assign it to array PTR. Well, because that's an array and I've declared it as such, C knows that I don't mean the value big array because there's 128 different values. What I really mean is the address of the first location of that array. So what's going to be assigned to that pointer is the address of that first location. That is exactly what the second statement is going to do. You'll notice in this case what I've said is go to the 0th element of the array, the first one, and get me its address by using the ampersand. So of course that will be the same address. In the next case, I have now used an index of 3. That really corresponds to the fourth integer in the array. There's one at index 0, one at index 1, one at index 2, and the fourth one at index 3. So how far down the array is that one? Well, this is where that pointer arithmetic becomes important. Since integers are of size 4 bytes, what I really mean is at 12 bytes past the start of the address is where that fourth element will begin. So the address that I generate here is FF000C. That C corresponds to 12 in decimal, 3 times 4 bytes. Okay? Now, that's exactly the same thing as the next statement. And why is that? Because in this case, what I've done is first taken a pointer to the first element and then said add 3. But remember, C knows that if we're adding to a pointer, we don't mean just add the value 3, but rather the 3 times the size of the data element, or in this case an int, 3 times 4. Okay, so now you can kind of see why C does this in its pointer arithmetic. What about the next statement? Here I'm just saying big array plus 3. Well, again, that's the same situation as the very first line, where we've taken big array to indicate just the first address of the array. And the plus 3, again, is to an address. We're adding 3 to an address, so we're going to multiply that by the size of the data item. All right, and this next example is a bit more complex. You'll notice that it's using 2 dereference stars, one on the left-hand side and one on the right-hand side. The one on the right-hand side is saying, get the value at array pointer and use that as an address and go get the value there. Well, what has array pointer been set to? Well, we had just set it to this address that ended in 0C. So we're going to go into that location, get the value stored there, add 1 to it, okay, and then where are we going to go put it? Where are we going to put the result? Well, the result, it says to go put in this at the same place where we got the value. So it says go to the address pointed to by address by array underscore PTR. That star in front, again, is saying dereference the value in array PTR and go to that location. Well, again, the value in array underscore PTR is 0C, so we're going to go to that location again. So what has this accomplished? Well, what this has accomplished is to increment the value stored in that fourth element of the array at index 3, but it has not changed the value of the array underscore PTR variable. That stayed the same and is still pointing to that address 0C. Okay, what about our next statement? You'll notice here we're trying to reference the 130th element of the array. Well, geez, our array was only 128. What happens here? Well, turns out C doesn't care. It just applies the same pointer arithmetic rules it did before. In this case, multiplying 130 by 4 and adding that to the starting address of the array. And will just give us an address that points to that location. That turns out to be out of the bounds of our array. We've gone 2 past the end of the array, but C doesn't check for that. And we'll see later on, other languages do, but C does not. And that's one of the dangers in using C. Now, the general rule here is that if I have an expression that looks like this, that is the same as saying big array plus I, because just big array by itself is the starting address, and plus I gets multiplied by the size of the element in the array before it's added to that address, so that it implicitly computes this expression, which you'll notice is the same thing, by saying the starting address of the array plus I times the size of the element in the array. Okay, and in C we can use the size of function to tell us what size the element of the array is. Okay, let's take a look now at strings rather than integers. A C-style string, a character string, is represented by an array of bytes. Each byte has a code in it, a 2-digit hex code, and one of the more popular ones is the ASCII code that uses 1 byte for each character. And here you see a map of most of the characters in the ASCII character set. And the way C indicates the end of a string is with a byte that only has the value 0 in it. So a string like Harry Potter, for example, would be represented by the following sequence of bytes. You'll notice that there is a byte for the space between the two names. The value, the code for a blank is 32 hex, and a 0 at the end signifying the end of the string. So the string Harry Potter is a 13-byte array, the 12 characters including the blank plus a 0 at the end to indicate the end. Now the reason we put a 0 at the end, often referred to as a null 0, is so that we can tell the end of the string. Right? How would we compute the string length if we were given the starting point of the string? We would move 1 byte at a time down the string and checking for a 0. When we find the 0, we would know we were at the end, and that's how we would compute the string length. Okay, because we're dealing with 1 byte at a time, we don't have to worry about issues of little endian or big endian when we think about character strings. So if we had the character string 1, 2, 3, 4, 5, it would actually be represented in precisely the same way in little endian machines or big endian machines. Now, later on we'll learn about Unicode characters that have more bytes per character. Unicode is a newer standard than ASCII that allows us to represent all the character sets around the world, and we need a lot more codes to do that for all the different alphabets that exist. So they can reach up to 4 bytes per character, and Java as well as C have libraries for Unicode, but Java commonly uses 2 bytes per character. That's sort of its default. So we'll see later the complexities of this, but for now strings are 1 byte per character. Okay, let's take a look at a C function that we can use to print out data that we store in memory by printing it out 1 character at a time, or 1 byte at a time, as 2 hex digits. All right. So here's a simple function written in C. It's called showBytes. It doesn't return a value, so we've put a void in front of it to indicate that. And then it takes 2 arguments. The first one is the address of the starting location in memory. So you'll notice it has a star there because it says this is a pointer to a location in memory. It is not a value. And to what kind of thing is it pointing? Well, it's pointing to a character. And in C, a car is a 1 byte quantity. So in this case, we're just saying we're pointing to a byte in memory. All right? And then the second argument is an integer that is the length of bytes that we want to print, the number of bytes we want to print. The body of the function is just a simple for loop that goes from 1 to length, or 0 to length minus 1, and increments the index by 1 each time around. That's what that I++ indicates, increment by 1. The body of the loop is a simple print statement that we'll see the format of in a second, but it prints two values. The first is an address, the second is a data value. You'll notice that we're using start, that pointer, so this is going to be an address, and then we're adding I, the index, to it. Since we're doing pointer arithmetic, what do we multiply I by? Well, since it's only pointing to a character, we multiply by 1 because characters are 1 byte. And then we print the data stored at that address by dereferencing that address. That's why we have the star on this side. So here we have the address, and here we have the data at that address. Our print format string says that we start off by printing a pointer. Okay, that would be that first element here, that address. So we're going to print a pointer, then we're going to insert a tab, then we're going to print the number 0 and the letter X. And we're going to do that to conform to C notation for hexadecimal values. And then the %.2x is a special notation for saying print a hexadecimal value of 2 digits, followed by a new line. That hexadecimal value of 2 digits is just the value stored at that address. Okay? The second element here in our print statement. Okay, so that's a pretty nice little function, and we can call it with anything actually, even integers, not just characters, because when we call it here, showing an example of another function that's going to show integers, we can call show bytes by casting the address of the integer as a character address. Okay, this is C casting. What we've done is said we have an address here, but it's the address of an integer. Can you please treat that as the address of a character, and then pass it to the function? Okay, and then the length here is just the size of the integer. So here we would expect to see 4 bytes that are going to be printed out by the function. Let's take a look at some sample executions of this function. Here we see the function, an integer 1, 2, 3, 4, 5 being placed in A, and when we call, we'll first print out that statement and then call the function showInt. So here's that first print statement directly from above that prints out the value. And then you'll see that inside of showInt, we've of course called showBytes, and it went for 4 bytes, printing out each one in turn, successive bytes at CC, CD, CE, and CF. And the rest of that address, is pretty arbitrary. Again, it's just where that integer A happened to be. And the integers, the values that got printed are 39, 30, 0, and 0 hex, which we know from previous examples are the hex representation of that value. Okay? So this is indicating that our machine is little endian because we saw the least significant byte first. And that's how we could write a simple program to check the endianness of our machine.